So neglecting the time dependence, the governing differential equation will now reduce to ordinary differential equation. So with time dependence, ignore this inertia term will vanish, and that will again in the domain omega x in the range 0 to L. So we can have this rearrange this and L minus x. So that leads to AE times du by dx is equal to plus C1. So that's the constant of integration. So integration of these terms, and then u will be equal to, or let us say okay, ux is equal to 1 over AE times integration second time minus x cube by 6 plus C1x plus C2, right? So this is the general solution, and specific solution will be obtained. I mean, these constants of integration C1 and C2 will be obtained by these boundary conditions. So when x at u at x is equal to 0, it has to be 0. So that means C2 should vanish, right? So if u at x is equal to 0, it should be 0. So that implies C2 should be equal to 0. And similarly, AE du by dx at x is equal to L, it should be equal to Q. So that should lead to the second boundary condition, the second boundary term. So that would be equal to, I would say, substitute AE times du by dx at x is equal to L. So substitute L here, x is equal to L. So L square minus L square by 2. So that is L square by 2. So minus QL by 2 plus C1. This is equal to Q. So C1 is equal to Q plus Q naught L by 2. That's the solution. So general solution that we can have here is ux is equal to 1 over AE times minus Q0 by L okay, 6 plus C1. C1 is Q plus Q naught L by 2. Multiplied by X. So that is the equation, the solution Ux. C2 is of course equal to 0 here, and at the same time let us, it is instructive, it is convenient to preserve the other quantity that will be of interest. Secondary variable variation is equal to minus Q0 by L to Lx minus x square plus C1, and C1 is Q plus Q naught L by 2. So these are the analytical solution, exact solution within the framework of theory of differential equations. Now I can look at solving these problems, and if you see, if we choose these terms, then we can actually plot the results and see how the displacement varies, how the axial thrust varies. You should appreciate that axial thrust varies in this case as a quadratic polynomial. The displacement varies as cubic polynomial within the domain 0 to L. That is obviously because of the fact that the differential equation is of second order. The governing differential equation is a second order differential equation, and the second order derivative term is equal to a first degree polynomial. So d2u by dx square is equal to some first degree polynomial. So double integration would of course lead to a cubic variation with respect to x, and that is what you are getting here, right? So true solution in this case, in this particular case, is displacement cubic variation, secondary variable varies as quadratic second degree curve. Now this can be higher, this entirely, you should appreciate that this variation is entirely triggered by the variation of q. If qx was varying parabolically here, then u would be varying to the degree of 4, fourth degree variation. Had q variation be parabolic variation or quadratic variation, right, varying with respect to x raised to the power 4, x raised to the power 2, then the displacement would vary as x raised to the power 4. So whatever be the variation of q, u is accordingly defined according to whatever is the governing differential equation. So this is something that you should appreciate here. And the secondary variable variation would be 1 degree lower because it is related to the first derivative, proportional to the first derivative of the displacement. So whatever is the variation of displacement, the axial thrust would vary 1 degree lower. polynomial variation of 1 degree lower than that of the displacements in this case, in this problem. Now, let us come to the weak form, or let us come to the approximate solution now. So, approximate solution, let us say ux is to be approximated as u hat x, and that leads to r omega residual, that is given by right and r gamma, I can write this as u hat x delta x plus ae So this is the boundary residual. So this all says that displacement is of course equal to residual, delta x, implies that this is the Dirac delta function acting at x is equal to 0. So all that it means is whatever is the value of x at x is equal to 0, that is the error in boundary term at x is equal to 0. And this represents whatever is the difference ae times du by dx at x is equal to L minus q. So that is the error in the boundary condition at x is equal to L. That's the Dirac delta function with argument x minus L. So that means this is the this function, this is the discontinuity at x is equal to L. So statement of weighted residual. W r omega d omega integrated over domain plus gamma w bar r gamma d gamma is equal to 0. So let us now expand this. What do we look at it? What do we get from this? So domain is of course 0 to L, W times d dx ae W bar multiplied by u hat x, this is to be evaluated at x is equal to 0 plus W bar ae this is to be evaluated at x is equal to L. This should be equal to 0. Now we can develop the weak form of the weighted residual. This is the strong form. Right. So let us just say This is the strong form. And now we can say weak form. Weak form will be when we treat the derivative here. So integration by parts on the first term. So we have w multiplied by ae times du hat by dx at x is equal to L minus w ae du hat by dx at x is equal to 0. So that's the boundary term minus integral 0 to L dw by dx ae du hat by dx plus integral 0 to L w multiplied by q naught by L multiplied by L minus x dx, and then we have these two boundary terms w bar u hat x at x is equal to 0 plus w bar ae du by dx minus q at x is equal to L. This whole thing is equal to 0. Right? So this is the weak form. Now the boundary term of the weak form represents this can be identified as the secondary variable, whatever is the coefficient of the weighting function term. So this is the secondary variable. Secondary variable is ae du by dx, and similarly primary variable is w converted into the unknown of the problem, so that is u. So essentially zeroth order derivative. So the form in which weighting function appears in the boundary term replace weighting function by the unknown function of the problem, so that is the displacement u. So u is the primary variable and ae times du by dx is the secondary variable. So the approximation has to be interpolation model in terms of the primary variable. Right? And now, what is the highest order of derivative in this expression, in the weak form? What do you see?
First degree.
Pardon?
The first order.
First order.
First order.
First order. So the only thing that I need here is u primary variable, that interpolation model in terms of the primary variable, that is u, it should be such that this derivative should exist. Du by dx should not vanish, so that this integral contributes to the approximation. Our approximation has some contribution from the to the error term, has some contribution to the error term, and that will help us in establishing the statement of minimization of error. If the approximation does not contribute anything towards error, how are you going to minimize that error, right? So therefore, this domain integral should exist, and in this case, the smallest or the lowest degree polynomial that will allow this domain integral to exist is first degree. Right? Even a first degree approximation for u hat would be enough to ensure that this integral exists. Right? So
Excuse me, sir.
yes,
Sir, if our u is a 2-degree parabola, then du by dx will there will be no du by dx. Then there is no weak form, sir.
if u is you are talking about u or q.
U, sir, u displacement u.
If displacement is a second order polynomial, then du by dx is of course first degree, isn't it?
Talking about such that if there is no du dx, for example, if u is 3 degree, for example, 2 degree means okay. Okay, sir. Sorry, sir.
Highest order of derivative in the weak form of weighted residual statement is 1, and that means approximation should have at least first order derivative non-vanishing. Right? So that means u hat, approximation for u hat can be a0 plus a1x. Right?
Sir,
Yes.
sir, suppose u is a second order polynomial.
Mm-hmm.
Then, in that case, that weak form has some added advantage or not? Like while I was doing that home assignment problem, that for the both formulation we are getting the same answer. So, what is the advantage of this weak form?
See, the advantage, first of all, advantage of the weak form is what you will see now is you have seen that the true solution is actually third degree polynomial. For the problem that we are dealing with, the true solution, analytical solution, is a third degree polynomial. But we are approximating that, we are trying to find an approximation using first degree polynomial. The highest order derivative that is required, continuity requirement, is just a first order derivative. So if I choose this by using only these two constant term and a linear term, the approximation condition is satisfied. Now this can be a good approximation, it can be a bad approximation, but the requirement of the approximation is satisfied. So the order of continuity requirement is reduced. First of all, it may be such that for some problems even the exact solution will be first degree polynomial, right? it can be possible that weak form and strong form will lead to identical solutions. That is also possible. That of course depends on what is the loading condition, loading pattern. Right. So, but weak form, the weighted residual statement includes the exact solution as one of the possibilities. There are infinite possibilities of approximation, and one of those possibilities include the true solution as well. So in some instances, you might get the true solution as well. But in general, the approximate solution from weak form will be uh, of lower order of continuity, lower or degree of smoothness compared to the true solution. But that is not a problem, as we will see. Our purpose is served very easily by these lower order approximations. So this approximation should have first order non-vanishing derivative. Okay.
Sir,
Yes.
so this U approximated function, it does not have only one requirement. Na, ki it should be differentiable only one time. It should also satisfy the boundary condition. And this function, it will not satisfy the boundary condition. Am I right, sir?
You are right in the sense of classical methods of approximation, and in that case we will choose this approximation according to the satisfaction of the boundary condition. A0 will be chosen so as to satisfy the essential boundary condition wherever it is. So in this case A0 has to be 0 because u hat of x should be equal to 0 at x is equal to 0, right? So we need to satisfy that boundary condition, so A0 will be 0 if we apply the boundary condition. And then this function, linear function, satisfies the boundary condition as well.
Yes, sir.
Right? But boundary conditions are handled differently in finite elements. So method of weighted residual, classical method of approximation, the trial functions themselves, I mean this approximation has to satisfy the boundary condition, at least the essential boundary conditions ab initio. But that is not the case in the case of finite element formulation. Finite element formulation, because the approximation is written in terms of the function value, right, primary variable itself. So this will be written as ui ni plus uj nj. So instead of a0 a1 we have these coefficients as the values of the function at nodes of interpolation. So the essential boundary condition can be imposed on these values at the time of solution of simultaneous equations. Right? So these are the values that if we prescribe these values, these are the essential boundary conditions, essentially. Right? So if we look at it, so this is the first order derivative, non-vanishing first order derivative for any one element, this first degree polynomial is defined by two nodes I and j, element E, and ni is of course defined as x minus xj divided by xi minus xj, nj is defined as x minus xi divided by xj minus xi. That's Lagrange interpolation formula, right? So if you look at it, So these are the first degree polynomial, both of them. So linear combination of them is also going to be first degree polynomial, and this is the standard form of that polynomial. So a0 and a1, you will find that they will be linear combinations of ui and uj, sum of ui plus uj and ui minus uj, something like that. I mean, if you collect the terms and try to rearrange it in terms of these, so you will find that these a0 and a1 can be written as a combination, linear combination of ui and uj. So this we can substitute, and therefore we can write here within the element, within element E. So this is equal to ui times x minus xj divided by xj minus xi minus plus uj x minus xi divided by xj minus xi, and accordingly we can also find the derivative du by dx, or instead of du by dx we should just say dni by dx is equal to minus xj, or xj divided by xj minus xi, and dnj by dx. So that is the derivative of this. So this is equal to minus of xi divided by xj minus xi. These will be used. We computed this because we will need these in evaluation of this boundary integral, domain integral, when we choose w as ni and nj. Right? So, any questions so far?
Sir,
Yes.
sir, do these infinite elements will satisfy compatibility?
Infinite elements. We are not talking about infinite elements here.
Sorry, sir, finite elements. Like number of finite elements are there. Are they
Yes.
going to satisfy the compatibility and uh, other
Of course.
laws of?
Of course. I mean, compatibility follows by using this interpolation model. That is the reason we adopted this model of approximate solution. So once the two elements, let's say, if this is one element and this is another element, right? So this is omega e and this is omega e plus 1. This node is common. Right? So approximation over omega e is given as an interpolation of the function values at this node and this node. Approximation over omega e plus 1 is given as the interpolation between this node and this node. I mean, I have drawn these two elements separately, but these nodes are essentially common. The finite element mesh looks like this. So this is the common node. So the primary variable is shared by the two elements. So once the primary variable is shared and it is an interpolation model, so obviously the function that is being approximated, u, is going to be continuous, compatible at this point, because The entire approximation is being developed in terms of that. And interpolation condition requires that whatever approximation has to agree with the value of the function at the node. So whether I approach this point from omega e or whether I approach this point from omega e plus 1, the function value is of course the same both uh, at the common point. So the compatibility is automatically guaranteed.
Sir,
Yes?
sir, if we had our u hat x as a naught x plus a1 x square, then how would we have returned this ui
That's
and
not
I?
allowed. You have to have complete polynomial. So you have to have complete all the terms. I mean a0 plus a1x plus a2x square.
Sir, if that was the case, then how would we have returned the u1 and ui and I form?
Oh, that's... Wait for the magic. Everything unfolds just like a magic trick. We will do that. Wait for tomorrow. Yep.
Sir, in other subjects like theory of vibration and geotechnical earthquake engineering, we dealt with fixed boundary problem like closed form solution, where these arbitrary boundaries are not have not been seen yet. Then, sir, how we are going to apply those finite element method there in those subjects?
Okay. I will give you problems dealing with vibration problem which needs to be solved using finite elements. Towards the end of the course, so that should allow you to understand how finite element method is used for vibration analysis.
And sir, I heard one more thing, that is discrete element method. And it has been written there that discrete element method considers compatibility between two elements, but finite element method doesn't consider that. Sir, why is it so?
That's not correct. You are actually stating the other way around. Finite element method does not consider the inter-element equilibrium, does not enforce inter-element equilibrium, but compatibility is always ensured. Distinct element method is essentially based on interaction between rigid blocks, and equilibrium is always satisfied. Compatibility is not enforced there. Right? You will always find distinct element method as rigid blocks, and individual rigid blocks, they are interconnected by normal springs, tangential springs, and so on, so that you have normal stress and tangential stress, shear stresses that are acting at the interfaces. So those are always going to be same, so that individual blocks, they remain in equilibrium. But if you look at it in finite elements, if you look at it in theoretically, they should be in equilibrium, but we do not enforce that equilibrium condition, and that is one of the things that we will study in this example problem. That is one of the key indicators of how good is your quality of approximate solution using finite elements. Right? So please go back to the source where you read about distinct element, and I am sure it is the other way around.
Sir?
Yes?
Sir, you rightly said now कि we have to consider a complete polynomial here,
Mm-hmm.
right? A naught plus a1x plus a2x square. Is it the same way for method of weighted residuals or any other method that we are considering?
Always.
We are not at all allowed to like have a like an incomplete polynomial or
See,
something.
you should always have as general solution as possible. You should have the possibility, all possibilities covered, and let the problem dictate the solution. If some term has to vanish, for example, if there is no component of solution along the linear term, that linear term coefficient will evaluate to be zero during the process of solution. You don't have to worry about it. If there is no linear term in the solution, that will be computed as a process of solution. But your approximation to start with should always have the all possibilities covered, whether it is constant term, linear term, quadratic term, or whatever, up to the highest degree, whatever you are considering.
Sir, but still we will get a solution. But the thing is that we won't be able to get a correct solution or a good approximation, right?
That's right. That's right.
Okay.
And
Okay.
there is no way. I mean, the whole point is approximate solution. It's a very dicey game, and you can actually be in for a very nasty surprises if you are not careful. Yes, Charu.
So then we can start with any degree of polynomial. Like if we have to consider on even small errors, then we can either start with x to the power 0.1, x to the
No.
power point.
No. No. It's all integer powers. We only look at the integer powers, and that too positive integers.
And sir, if we have those integer powers, x square, x cube, x and so on, then why do we have another option like cosine and sine function there?
In
How they are different from-
finite elements we do not.
But sir, in the strong form, we have used as
That was-
approximate function as cosine.
Yes. I started that using sine and cosine because all of you are familiar with Fourier series approximation.
And sir, why we don't use that?
Why we don't use that? The reason is it is sine and cosine, they are not always easy to generalize. I mean, the Fourier series expansion, if you look at it, there is a choice of fundamental period, fundamental harmonic, that depends on what is the period of the function that is to be approximated. Right? So everything depends on the multiple of that fundamental harmonic. There is no such restriction in the case of choice of polynomial. So the choice of polynomial lends itself to a very systematic process which is well suited for automatic computation with very little human intervention involved. With trigonometric functions, you need to define what is the frequency.
And sir, for that we must be having knowledge about the function we are going to approximate.
So that becomes the case dependent. So it cannot be made as a, I mean, we look at it as a commercial point of view. It cannot be produced as a kind of standard software which will be able to handle all possible situations.
Sir, does this mean that we cannot even use exponential functions here? Like only the polynomial function must be
Not in general finite element analysis. Specific cases, of course, local enrichments are possible, and special purpose elements are used for some special cases. So that is possible, but not as a standard package, standard software tool. And many times it is not even required. All these variations can be approximated, can be captured by polynomial approximation themselves. We will see that. What you are referring to as fractional powers, that fractional power can be generated by using these standard finite elements as well. So the theory is very rich and the possibilities are immense. And that's the reason finite element method is such a powerful tool. It's almost a de facto standard for engineering analysis now.
Okay, sir.
Okay, so we will continue from this point in our tomorrow's lecture.